Welcome. So in the last lecture we have discussed about what is a crisp set, what is a fuzzy set, and towards the end we have discussed the membership function, introduction to membership function, and what type of values the membership function can take. It can take both discrete values and continuous values depending on the type of the membership function. So these things we have discussed in the last lecture. In this lecture, we'll be discussing few fuzzy terminologies and we'll be exploring further about membership functions. Okay. So let us discuss some fuzzy terminologies first. So to start with, we'll be discussing something called a support. So what is a support? So support is defined something like this. The support of a fuzzy set A is a set of all points x which belongs to some universal set such that mu a of x is greater than 0. So this mu a is nothing but membership function. This mu a is nothing but membership function. Okay. So x can take anything. So if you take this as the plot, okay, you plug some values for x. Say for example mu a of 1. So in that case x is 1. Okay. So for that if you got 0.5, okay, then mu a of 2, say for this you got, we are not discussing the function, it may be some function, say you got 1.5. Mu a of 3, for this if the result is 2.5. Mu a of 4, for this if the result is 0.75. Then the support of a fuzzy set A is a set of all points x whose membership values are greater than 0. Now for these 4 values of x, only for these two things it is greater than 0. Okay, remaining it is less than 0, right? So the set of all points of x for which it is the membership value is greater than 0, so those points comes under support. So in this case it is only 2 and 3, right? So this is how support is defined. So basically the content of a support is a crisp set. Okay, the support of a fuzzy set A is a set of all points x belonging to the universal set such that the membership function of x will be greater than 0, but the resultant set will be a crisp set. Okay, because it has some what you call fixed values. There is no overlap in this, right? Okay, so this is how support is defined. Next, core. What is a core? The core of a fuzzy set A is a set of all points in x, again such that x belongs to the universal set x, such that mu a of x is equal to 1. Again mu a is nothing but membership function. So when you apply x to a membership function, for whatever the value of x you got the result as 1, those points of x will be called as core. Okay, so here is a simple example. Say assume this is the result of a membership function. So if you see these are the values of x. Okay, so let us assume this is 1 0, this is 0 1 2 3 4 5 6 7 8 9, so on and so forth. So for the value of 1, the membership function is 0. Actually this is how the membership function behaves. Okay, so 0 it is 0, 1 it is 0, 2 also it is 0. Okay, say, but for 3 it is 1, for 3 it is 1. Okay, for 4 it is 1, for 5 it is 1, for 6 it is 1, for 7 it is 1, again for 8 it is 0. Are you getting? So what are the set of values for which the membership function is resulting in 1? Those set is called as core. Okay, so core of a fuzzy set A is a set of all points in x such that the membership function will be resulting in 1. So this is how the core can be represented. Core of A is equal to x such that mu a of x is equal to 1. Next, normality. What is meant by normality? A fuzzy set A is called as normal. A fuzzy set A is called as normal if its core is not empty. A fuzzy set A is normal if its core is not empty. What is core? In the previous slide we have discussed. What is core? Core means the core of A. The core of a fuzzy set A is a set of all points x such that mu A of x, that is the membership function of x, is equal to 1. Okay. Now we are discussing normality. A fuzzy set is a normal if its core is not empty. That is if it has at least one value in the core. Okay. So this, for example, this particular fuzzy set is also normal. This particular fuzzy set is also normal because why it is normal? Because what is its core? Its core is not empty. Its core is, these are the values 3, 4, 5, 6, 7. For all these values of x, it is resulting in the value of 1. The membership function will give an output 1. So the core is not empty here. Okay. So as the core is not empty, it is also a normal set. But if for some function, if the core is empty, then we won't call it as normal. In that case, the normality will be false. For example, you take this particular membership function, say some membership function, it is behaving like this. This is how it behaves. Okay. This is this, so its peak point, if you see, this is, say maybe this is 0.5 because 1 is here. So there is no point which is reaching up to 1. Maybe this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth. So if you see here, is there any point of x where the membership function is resulting in 1? No. So what is its core? Its core is empty. It's nothing is in the core. Okay. So a fuzzy set is normal if its core is not empty, but in this case the core is empty. So in this case the normality of this particular set is false. It is not normal. Okay. So this is how normality is defined. And then crossover point. What is a crossover point? Okay, a crossover point of a fuzzy set A is a point x such that the membership function will result in 0.5. So what are the set of points for which the membership function is resulting in 0.5? Those point of x were called as crossover points. Okay. So crossover point is the set of points in x whose membership function will be 0.5. So it is given like this: crossover of A is equal to x such that mu A of x is equal to 0.5. So if you consider this as a membership function, then in this membership function you can see, so these are the values of x. So 0, say 0, 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. For 0, the membership function is giving 0. For 1, it is 1. For 2, it is somewhat here, maybe 0.1. Okay. For say 3 is here. For 3, it is giving 0.5. Okay. For 4, it is giving here maybe 0.8. For 5, it is 1. Again for 6, it is giving 0.5. Okay, right? So these two are the crossover point. For 7, again it is 0.1. So this and this are the crossover point. That is the values of x for which the membership function is producing a value 0.5. Such points are called as crossover point. Okay, the value of x for which the membership function is producing a result 0.5. Such points are called as crossover point. Okay, right? So these terminologies you should remember. Next, fuzzy singleton. What is a fuzzy singleton? So this is another terminology. A fuzzy set whose support is a single point in x. Okay, whose support is a single point in x with mu A of x is equal to 1 is called as a fuzzy singleton. Okay, what does it mean? It means that when a fuzzy singleton is a set, we call a fuzzy set as a fuzzy singleton set if there is only one value of x. If there is only one value of x which is producing an output of 1. Okay, then such a set will be called as a fuzzy singleton set. Is it clear? A set will be called as a fuzzy singleton set if there is only one value of x whose membership function is resulting in 1. Say for example, this particular, say, membership function is behaving like this. This is not a continuous function, it's a discrete function. So let us assume these are the x values, say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay. For 0 it is giving a value 0. For 1 it is something here 0.4. Okay. For 2 it is something here say 0.7. For 3 something here 0.8. Okay. For 4 alone it is giving 1. There is no other value of x for which the membership function is resulting in 1. For 5 it is 0.5, 6 it is 0.4, 7.3, 8.3, 9.2, 10.1. So there is only one point of x which is resulting in a there is only one point of x when it is applied to the membership function, it results in 1. So in a fuzzy set, if there is only one point which is producing an output 1, then such a fuzzy set is called as a fuzzy singleton set. So this is actually a singleton set because there is only one point which is producing output of 1. Say for example there is another point 10 also producing the same output 1, then in that case you won't call this as a singleton set. Okay, singleton means only one x will produce an output of 1. Okay. Right. So next we will be discussing something called as alpha cut and strong alpha cut. So when you will, what is an alpha cut and what is a strong alpha cut, right? There are two things, alpha cut and strong alpha cut, right? So the alpha cut of a fuzzy set A is a crisp set. The alpha cut of a fuzzy set A is a crisp set. Actually it's a crisp set, and it is defined by something like this, that is A alpha is equal to x. A alpha is equal to x such that the membership function of x will be greater than or equal to alpha, right? So say for example, say for example, already you have a, a fuzzy set, okay, with different membership with different values for the membership functions. Okay, so alpha cut means a, for example a alpha is equal to x such that when you apply this to a membership function, you take only those values which are resulting greater than alpha. For example, if it is a2 means we take only those values which are producing a value which is greater than or equal to 2, right? Say for example there is a membership function and say x is equal to 1. When you apply this to the membership function, say the result is 0. Okay, so when you apply 2, say the result is 1. So when you apply 3, say the result is 2. When you apply 4, okay, say the result is 5. When you apply 5, say the result is 7. So a2 means what? A alpha means what? It will take only those x which are producing a membership function value which is greater than or equal to alpha. A2 means it will take only those values which are producing a membership value which are greater than or equal to 2. So in this example, if you see which or the x which is producing value greater than or equal to 2, x1 it's not greater than 2, so we cannot take it. X2, when x is 2 it is not greater than or equal to 2. X is 3, yeah, it is equal to 2, so you take this 3. X4, is it greater than or equal to 2? Yes, so 4. X5, when x value is 5, the membership function, is it resulting in greater than or equal to 2? Yes, so take this. Okay, so these are the values which comes under the alpha cut. Here the value of alpha is 2. Okay, what is alpha? In this case alpha is 2, right? So this is called as alpha cut. What is strong alpha cut? It is very similar. Strong alpha cut is represented as a dash of alpha which is equal to x such that the membership function will result in a value greater than alpha, whereas alpha cut is greater than or equal to alpha, whereas strong alpha cut is greater than alpha. So what will be a dash of 2, that is strong alpha cut in this case? So 0 is not greater than 2, 1 is not greater than 2, 2 is also not greater than 2, so this also will not come under strong alpha cut. 4, for membership value, for x value of 4, the membership function is 5, this is greater than 2, so 4 will come here and 5 will come here, right? So this is how alpha cut and strong alpha cut is defined, right? So what you can say in the sense, what if you recall what is support, the first terminology that we have discussed is support. What is support? So support represents all values of, what do you call, support represents all values of x whose membership function is greater than 0. Okay, so support of a is, you can say it is nothing but a dash of 0, because a dash represents what? Strong alpha cut. Okay, so strong alpha of 0 means whichever the membership function which is greater than 0, that will come under this. So support of a can also be called as strong alpha of 0. Okay, similarly core of a is equal to a1. So what is core of a? So core represents all values of member function which is greater than or equal to 1. Okay, so 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 core of a uh, so so core of a means what? Previously we have defined core of a. Yeah, core of a means a set of points in x such that the membership function is equal to 1. That is core of a. Okay, so yeah, 1 minute. Yeah, so core of a, you cannot call it as a1, but for that particular graph, whatever in this particular graph, whatever we have discussed, so in this case you can say that core of a is equal to a1, because here there is no values of x which is producing a value which is greater than 1. It's always equal to 1. Okay, so this is about what you call alpha cut and strong alpha cut, right? Next we'll be discussing something called as bandwidth. So what is bandwidth? So bandwidth is actually the difference between 2 points x1 and x2, such a way that the membership function of x1 and x2 should be equal to 0.5. So previously we have discussed what is 0.5. 0.5 is nothing but crossover point. 0.5 is nothing but crossover point. Okay, so bandwidth is defined as the distance between the two unique crossover points. Okay, it should not be same crossover point, two different crossover point. Okay, that is this point also producing a membership value of 0.5 x1, and this also producing a x2 also producing a value of 0.5. Then the difference between these two, that is called as bandwidth. Next we will be discussing something called as symmetry. So a fuzzy set A is symmetric. A fuzzy set A is symmetric if its membership function is around a certain point x is equal to c, namely mu a of x plus c is equal to mu a of, this is c minus x. Okay, not x minus c, this is mu a of c minus x. Okay, for all x belongs to x. Okay, so we can better understand with this diagram. So let us assume a membership function is represented like this. That is, this is the value it gives. Okay, that is, so this is x as usual. So this is, all these are 0. All these are also 0. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that is when the x value is 0, the membership function will result in 0. When x value is 1, the membership function will result in 1. When x value is 2, the membership function is result in 0. When x value is 3, say it is coming here. Say this is, let us assume this is 2. Okay, let us assume this is 2. Okay, when x value is 4, it is coming here. Okay, so this is 1, so this cannot be 2. So let us assume this is 0.2. Okay, say this is 0.2. Okay, 0.2. So when x is 4, say this is 0.5, it is coming here. Okay, 0.5. When x is 5 also, say it is 0.2. Okay, when x is 5 also it is 0.2. Okay, when x is 6, let us assume 6 is here. Okay, 7 is here. When x is 6, let us assume it is 0. Okay, so this case is called as symmetric. Why it is symmetric? Because this c is what value of x? C is the center point. C is nothing but when x is equal to 4. So whatever you see left to the c, and whatever you see to the right of the c, both are actually behaving in the same way, right? That is, c minus c is 4, right? So x is equal to 4, which is equal to c. C, say this is the center point. C minus 1 is what? 3. So 3, when you apply to the membership function, is giving 0.2. C plus 1 is what? 5. When you apply this to the membership function, it also gives the same value 0.2, right? Similarly, C minus 2 is nothing but 2. So when you apply this to the membership function, it gives 0. C plus 2 also it gives 0. So like that, anything you subtract from C, it behaves in the same way. Okay. In that case, we call it as it is symmetric. Okay. Now you see this definition. A fuzzy set A is symmetric if its membership function is around a point C such that the membership function of x plus C is equal to the membership function of C minus x, right? So in such case, we call that membership function as symmetric. Next, let us try to understand what is meant by a open set, what is meant by a closed set. Okay, so here you can see there are different graphs. First, let us take this graph alone, this curve alone. Okay, so this is actually an example of open left. To the left it is open. Okay, to the right it is closed. That is, say this is x. That is when the x is going towards, if this point is 0, then this is what? This is x is going towards negative. Okay, that is when x is going towards minus infinity, it is 1. Say this point is 1. So as x move towards minus infinity, as x move towards minus infinity, the output will be, the membership function will be always resulting in 1. So such membership function will be called as open left. Okay. Similarly, if you see this one, but let us take this also. So here, as x goes towards positive infinity, see this membership function you can extend like this. As x goes towards plus infinity, it becomes 0. The membership function will result in 0. Are you getting? So it is open to the left, but it is closed to the right. So such membership function are called as open left. Okay. Right. Now let us take this one. Let me take different color. Okay. Now let us take this one. This is actually open right. This is open right. So here it is becoming 0. Okay, that is, so this is again, it is to the infinity, minus infinity, right? As x approaches minus infinity, this membership function will result in 0. As x approaches positive infinity, plus infinity, this will result in 1. Okay, so such membership function is called as open right. The next one is the middle one, which is actually a closed membership function. So if you see this particular membership function, how it behaves. So as x goes towards minus infinity, it is becoming 0. As x goes towards plus infinity also, it is becoming 0. So such membership function are called as closed. That is, some value of x, it will give positive output. Okay, for all other values, as x move towards minus infinity and as x move towards positive plus infinity, it will give 0, right? So that is what is represented here. Open left means what? If x tends to minus infinity, open left, you see, if x tends to minus infinity, then the membership function will result in 1. As x tends to positive infinity, the membership function will result in 0. That is open left. Open right is opposite to that. As x tends to minus infinity, it will result in 0. As x tends to plus infinity, it will result in, the membership function will result in 1. For closed, this is the one closed. For closed, as x tends to minus infinity and as x tends to positive infinity, it will result in 0, right? So this is another terminology which is about open and a closed fuzzy set. Okay. So then let us try to understand the difference between fuzzy logic and probability. See, fuzzy logic actually it is not same as probability. It is quite different from probability, but there is some similarity. So if you take probability also always takes values between 0 to 1. So fuzzy also always takes values between 0 to 1. But that doesn't mean that fuzzy logic is same as probability. So there is a lot of difference. So I would like to leave it as a homework. You try to identify the difference between fuzzy logic and probability. Okay, because this is something which you have to refer certain things, many things, and you have to understand. Okay, because this understanding is crucial to to have a better understanding of this course. Okay, so here is an example. Say a patient come to the doctor to diagnose a disease. Okay, so the doctor is prescribing a medicine with a certainty of 60 percentage. Okay, that the patient is suffering from flu. Okay, that is the doctor is predicting that the patient is suffering from flu, but his prediction is how much accurate it is, in the sense it is 60 percentage accurate. Okay, so the disease will be cured with a certainty of 60 percentage. That means that means 60 percentage of the time the disease will be cured, but there is an uncertainty of 40 percentage. Okay, but actually this is actually an example of fuzzy. Okay, so there is no certainty, so there is a degree of uncertainty. Okay, in fuzzy always there is a degree of uncertainty. Okay, whereas in probability, when we say that about a chance of an event to occur. Okay, what is the probability that an event will occur? Say here is an example. India will win the T20 tournament with a chance of 60 percentage. Okay, so it means that what? It means this is not a prediction. This is actually based on some past data. This is based on some past data. What is the past data? That is previously out of 100 matches India has won 60 matches. Okay, so we say that, so based on the past figure, we are saying that it will win. Okay, there is a chance of 60 percentage. Okay, whereas this and this were totally different. Okay, right. So you can also say that uh, the fuzzy and the probability is somewhat connected to prediction and forecasting. Okay, so if you say prediction, when you see prediction, it is actually fuzzy. It is guessing. It is guessing about the future based on your experience. Okay, prediction is guessing, best guess based on your experience, whereas forecasting is actually based on probability. So when you take the information from the past job and apply it to the new job. Okay, so weather forecasting, so that is actually, it's not a prediction, it is forecasting. So say for example, if you see the weather forecasting, it will say that next 10 days the weather of Hyderabad. So how they get that? So that is by analyzing the data of last 5 years or last 10 years. So last 10 years in the month of June 1 to 5, what is the weather? So based on that they say, right? So that is not prediction, that is forecasting. So for forecasting, probability is used, and for prediction, fuzzy logic is used. Okay, right. So as we have already discussed, the membership function can be either discrete or it can be continuous. So this is an example of a discrete membership function, where there are, say for example, this is 0 1 2 3, there are discrete values, it's not continuous. Okay, in between there is nothing. Okay, whereas this is a continuous membership function. Okay, right. So now let us discuss something more about membership functions. There are different types of membership functions, and let us try to understand what are the normally how a membership function will look like. So this is one type of membership function. So here this axis is x, and this is the result of the membership function. So this type of, the membership function is of this shape, then we call it as a triangular membership function. If the membership function is of this shape, then we call it as trapezoidal membership function. If the membership function is like this, so this is actually bell curve. Okay, so this is actually a bell curve. So if it is like this, then we call it as curve. Simply we can call it as curve. Okay, if the membership function is like this, then this is something called as non-uniform membership function. Okay, so this is also an example of non-uniform membership function. But another thing you can observe here, this is open left. Okay, this is open right, and this is the closed one, right? Okay. So now, so this is through the graph we have discussed this membership function, like triangular membership function, how it will look, trapezoidal membership function, how it will look, and curve membership function, how it will look, all these things. Now let us try to define them mathematically, right? So when you say a triangular membership function, as we have already discussed, it is something like this, but this can be represented mathematically like this: triangle of x, that is x represents this point. Okay, whatever the value x will take, such that A, B, C. It uses three parameters A, B, and C. What is B? B is nothing but this center point of the triangle. Okay, is A is this point and C is this point. Okay, so so triangle of x a comma b comma c can be given like this. So that is, if you see any value of x which is less than a, any value of x which is less than or equal to a also it will result, the membership function will result in what? 0. Okay, so if x is less than or equal to a, the membership function will result in 0. If x is greater than or equal to c, then also the membership function will result in 0. That is, if c less than or equal to x, this is nothing but what? X is greater than or equal to c. Either way you can write. You can call either c is less than or equal to x, or you can say x is greater than or equal to c. In that case also it is 0. Otherwise, if x is greater than a and if it is less than c, then it will have some value. Okay, so how? So again the values will differ. For example, if x is greater than a, okay, and if it is less than b, if it is somewhere here, okay, then this is the value it will take. Okay, that is, if x is falling between a and b, then this is the value it will take, x minus a divided by b minus a. So basically this is, we are calculating the value of this slope. Okay, so whatever the value of x minus a divided by b minus a. Similarly, if x value is falling between here b to c, okay, then it will be c minus x divided by c minus b. Okay, so this is how this triangular membership function can be represented mathematically. Similarly, trapezoidal membership function can be represented like this. Here we use 4 parameters a, b, c, and d. So this is a trapezoid shape. So this is a, this is b, this is c, and this is d. So again you can see this as a triangle. Okay, this is one triangle, and this is one triangle. Okay, so here for any value of x which is less than or equal to a, it will result in 0. Okay, similarly any value of x which is greater than or equal to d, okay, whether d less than or equal to x, you can say, or you can say that x is greater than or equal to d, it will result in 0, right? And for any value of x which is in between b and c, it will result in 1. So for all these things it is 1. Okay, that is, any value of x which is in between b and c, it will result in 1. Okay, so if x is between b and c, that is including b and c, then it will result in 1. Okay, if x is in between a and b, then again you can apply that what you call the triangular membership logic. That is it will be x minus a divided by b minus a. Similarly, if x is between c and d, then it will be d minus x divided by d minus c. Okay, so this is how the trapezoidal membership function is defined. Next, Gaussian. So this bell curve, whatever we have discussed, that is called as the Gaussian membership function. So in a Gaussian membership function, for x we take two things. One is c, the center point. The another one is sigma. Okay, how we got this sigma? So c is the center point of the Gaussian function. Okay, this point, that is c, and this sigma, there are how we got, in the sense, for the, with this c you multiply 0.1, with c you multiply 0.1. okay, then you will get one value, right? Similarly with c you multiply 0.9, then you will get another value, right? So this the what you call the distance between these 2 points, that is nothing but sigma. Okay, and this is given by this equation. The Gaussian membership function is given by this. This is one of the most famous membership function. So it is something like a formula, you have to remember it. Okay, e to the power minus 1 by 2 then x minus c divided by sigma the whole square. Okay, but you can have a little knowledge, that is, so the point is, the Gaussian membership function is something like this. Okay, this center point is nothing but what? C. So with this center point you multiply 0.1, that is 0.1 c, and 0.9 c. Okay, so then you got some point. Okay, so that difference, the distance between these 2 points is nothing but the sigma, right? Okay, so, and this is given by this equation. You should remember this. Okay, right? So this is so as this Gaussian function is important, we'll be discussing some more detail about this. So this Gaussian function is otherwise called as bell curve. Okay, so this is otherwise called as what? Bell curve. So both Gaussian function and bell curve, actually it represents the same thing. It can also be called as bell curve. Okay, so this is a generalized bell curve, it is also called as Cauchy MF, that is Cauchy membership function. MF stands for membership function. So in that case it is represented like this. There is bell of x, a, b, c. There are 3 points, a, b and c. C is the center point again, okay, and and a is some value such that you subtract that from c, okay, and also you add that to c. So what you get that point, okay, you get 2 points. When you subtract a from c, you will get 1 point. When you add a to c, you will get another point, okay, right? And b is this, okay. So b is this distance between c minus a to c plus a, that is b, right? So this slope, so this point, this slope at x and slope at y, okay, this slope at x and slope at y is given like this. Slope at x is nothing but b by 2a, slope at y is minus b by 2a, okay. And this Cauchy membership function is given like this. Bell of x a b c is equal to 1 by 1 plus x minus c by a to the power to b, right? So this represents that if it results in some negative value, it will just take it as a positive one, right? That is, the sign will be ignored, okay, and 2 to the power b, right? So this is a generalized bell curve which is called as Cauchy MF. So we will be discussing some examples based on this. So we'll be revisiting this again, right? Okay. So this is again for this generalized membership function. Say for example this Cauchy MF. If you apply a is equal to 1 and b is equal to 1. If you apply a is equal to 1 and b is equal to 1, then this is what you will get, okay. So when you apply a is equal to 1 and b is equal to 1, so this is what you will get as a result, okay. So that is and c is 0. So this is the, I mean this point is x axis 0, okay. And when you say a as 1, then it is 0 minus 1 minus 1, okay. 0 plus 1 is plus 1, and this b also, if it is 1, then this is what it will look like, okay. So this in this Gaussian in this generalized bell curve, by changing a, the shape of the curve can be changed by changing a and b. Not only a, by changing a and b, the shape of the curve can be changed, okay. That is, by changing a, the curve can become like this, similarly like this. By changing b, it may become like this, right? That is, okay. So so similarly, by changing a and b, you can also change the shape of the curve, right? Okay. So next we will be discussing sigmoid. So sigmoid membership function, this is also an important function. This is used in deep learning also, okay. So in a sigmoid membership function, for a given x, we take 2 parameters a and c. So c is some point in x. So let us assume c is 1. Let us assume c is 1. Okay, and let us assume a is 0.5. When a is 0.5 and c is 1, so assuming a as 0.5, okay, and assuming c as 1, if you apply different value of x, say if you apply different value of x, like you say that x is minus 0.5, minus 0.4, minus 0.3, minus 0.2, minus 0.1, 0, 0.1, 0.2, 0.3, 0.4, 0.5, so on and so forth. If you keep applying, then this is what the curve you will get, okay. That is, this is what the curve you will get. That is that exactly when, that is when a is equal to that is a is 0.5 and c is 1, then you apply different values of x, okay, then this is the curve you will be getting. That is this what you call the a is nothing but the slope, okay. The value of the slope will be 0.5, okay, right. So I mean the curve will exactly pass through this point, okay, exactly pass through this point of y-axis, which is 0.5, okay. Say for example a is 0.3, instead of 0.5, if you apply 0.3, then maybe say assume this is 0.3, this is 0.3, then your curve will be something like this. Are you getting? It will be like this. Okay. So if a is 0.7, then it will cross over here. Then the curve may be something like this, right? So depending on like where you want to cross over, accordingly you can fix the value of a, and also you can change the value of c. Okay, so here this c is nothing but what? This is x value of 1. Okay. Similarly, if you want to shift this entire curve to the right, okay, if you I don't want the curve here, I want the curve here, then you shift the c. Instead of c keeping as 1, you keep it as 4, then the curve will come here, right? If you want to shift the curve to the left, then you decrease c, you make c as -2, something like that, right? So that is what it says. Okay. So sigmoid is given by this particular formula. Sigmoid x of a comma c is equal to 1 by 1 plus e to the power a by x minus c. Okay. So this is otherwise called as x curve, s curve. Okay, because you can see this, the shape of this curve is what it is like a s shape. Okay. So it is also called as s curve. Okay. So right. Now let us take another example. Say considering these grades of the student. So student who got more than greater than or equal to 90 marks is excellent, and these are different ways of categorizing the students, like grades 75 to 90 is very good, 60 to 75 is good, 50 to 60 is average, 35 to 50 is poor, less than 35 is bad, right? But this is not a fuzzy classification, this is a crisp classification. So this is a crisp classification, but now when you apply it on a fuzzy, it will be, maybe it may be something like this, depending on the membership function. Okay. So currently you don't see these red curves, you ignore these red curves. If you ignore these red curves, then this is nothing but a crisp thing. So less than 20 it is bad, 20 to 30 it is poor, 30 to 50, okay, 30 to 50 it is what you call, yeah, 30 to 50 is average, right? And 50 to 60 is good, right? 60 to 80 is very good, or greater than 60 to 80 is very good, greater than 80 or greater than 90 is excellent. Okay, right? So I don't know whether it is matching with this definition or not. Greater than or equal to 90 is very good, greater than 75 and less than or equal to 90 is, greater than or equal to 90 is excellent, right? Greater than or equal to, greater than 75 and less than or equal to 90 is very good. Okay, so greater than or equal to 75, okay, this is some crisp definition, it may not be matching there, but here you have the membership function. So these are different membership function, so let me use different color. For example, this is one membership function. Okay, so one membership function is given like this, right? Similarly, there is another membership function. So this is another membership function. This is another membership function which is represented like this. Okay, so maybe like that there are many membership function, here it is defined. Okay, just for our understanding. So this is another membership function which is behaving like this. Okay, so like that there are different membership function. Okay, so if you take this particular membership function, see, this is the universal values. The universal values is ranging from 0 to 100. Okay, but this membership function, it corresponds only up to the value of 40. Okay, that is anything less than 20, this membership function is going to result in 1. Okay, which means that it is going to say that that student is poor. Okay, if anything greater than 20 to 40, it is going to result like this, these values. Okay, if anything greater than 40, it is going to result in 0, nothing, it is not, it is closed here, there is nothing, right? Okay, so this membership function, it is used to categorize only bad and poor. Okay, right? Similarly, if you see this membership function, okay, so here you can see Okay, yeah, let us not go there. That is crisp. Okay, so similarly here, if you take this particular membership function, it takes values only between 20 and 40. Okay, that is anything less than 20, it will produce 0. Anything greater than 40 also, so it is this 20 to 50. Anything greater than 50 also, it will produce 0. So between 20 and 50 it will produce some values. Okay, so actually basically it is dealing with what? It is dealing with poor and average. Okay, similarly if you take this membership function, anything less than 30 it will give 0, anything greater than 60 it will give 0, between 30 and 60 it will give some values, right? So basically it is talking about average, right? So like that, we can use different membership function to categorize different category of students uh, with overlap. Okay, here it allows overlaps, right? That's the main point. So that means that, say for example, uh, so this particular student, they are coming in this group of students, they are coming in poor and also average, right? So they are covered in two membership functions, the students who are coming in between here, this range 30 to 40, right? So when you use this membership function, they will be classified as poor, but when you use this membership function, they will be classified as average, right? Okay, so these things we'll discuss later, but before that there is something else we want to discuss. Hmm. Okay, so there is something called as concentration and dilation. So we'll be discussing what we'll be trying to, let us try to understand what is meant by concentration and what is dilation. So so concentration is given like this. That is you can create a new fuzzy set a to the power k, such that a to the power k is equal to membership function of x, uh, the result of membership function of x to the power of k. So what does it mean? It means that already you have a membership function, already you have a set, already you have a fuzzy set, okay, whose result is nothing but mu a of x. Okay, that is, say you have a fuzzy set a, you have a fuzzy set a, and this fuzzy set contains some values like a1, okay, a2, a3, up to an. How you got these different values? In the sense, when you apply, say for example, one particular value to this particular membership function, when you apply x1 to membership function, you got a1. Similarly, when you apply x2 to this membership function, you got a2. When you apply x3, you got a3. Like that, you got up to when you apply xn, you got an. Okay, right? Now already you have these membership functions. Okay, now for now from this membership function, we are going to derive another membership function. Okay, that is, you can create like what you call, you can create another membership function called a to the power k, such that what is a to the power k? In the sense, it is mu a to the power x1 to the power of k, whatever the result of this, that will go here. Okay, maybe this is a1 to the power k. Similarly, mu a to the power mu a of x2 to the power of k, that will be maybe a2 to the power of k. Like that you will create up to an to the power of k. Okay, so that means from an existing fuzzy set we are creating a new fuzzy set. So that is called as concentration. That is called as concentration. Okay, so dilation is also basically, it is a it's a new fuzzy set which we are creating, but the difference is what? Here this, in case of concentration, this value of k will be greater than 1. In case of concentration, this value of k will be greater than 1. If k is greater than 1, then we say it is concentration. Okay, in case of dilation, a to the power k is equal to mu a of x to the power k, where k is less than 1. If k is less than 1, then we call it as dilation. Okay, so normally why it is used, in the sense, as we already discussed, it is used to create more fuzzy sets from an existing fuzzy set. Okay, so concentration is something like what you call, it is something like increasing in positive direction and dilation is something like increasing in the negative direction. So let us try to understand this with an example. Assume there is a fuzzy set age which contains these values: young, middle aged and old. Okay, now again for these things you can create a separate fuzzy set. For young, for example, you can create something like this. You can create another fuzzy set which includes young, so something like not young, very young, not very young and so on. Are you getting? Similarly for old, you can create another fuzzy set, something like this: old, very old, very very old, extremely old, like that. Okay, so here if you see, very old is something, uh, what you call, greater than old. Okay, and very very old is greater than very old, and extremely old is greater than very very old. Are you getting? So so this is called as concentration. Moving from one level to another level, that is called as concentration. Okay, moving from one level to the previous level, that is called as dilation. Okay, for example, if you already defined old, then extremely old can be defined like this. Extremely old is nothing but old to the power 2. Here k value is 2, k should be greater than 1, right? So old to the power 2 will be what? Very old. Okay, that to the power 2 will be what? Very very old. That to the power 2 will be what? Extremely old. Okay, so now we want to, already you have defined old, now we want to define more or less old. It means is not somewhat old, is less than old. Okay, is someone who is little less than old, then it is old to the power 0.5 is less than old, so that means k less than 1, right? So when you want to move in the in the positive end, then you have to use concentration. When you want to move in the negative end, you have to use dilation. Okay, right? So again, here is an example for whatever we have discussed previously, the open curve, closed curve. I mean, this is open left, this is open right, and this is the middle one is closed. Here is an example with some values plugged here, right? Say for example, this particular curve, it represents young. Okay, this curve, it represents old. Okay, so then the membership function mu represents membership function. Membership function of young is given like this: bell of x comma 22 comma 0. So if you recall from the previous thing, whatever we have discussed, that generalized bell curve, okay, that Cauchy curve, this is x, this is a, this is b, and this is c. So if you recall from that, I will try to draw here. So the curve will be something like this. The curve is something like this. So this point is nothing but this point is nothing but c. Okay, so then we take some point here which is c minus a, and we take some other point here which is c plus a. Okay, and it will cut here somewhere on the graph, so that this point is nothing but b. Okay, so here we take 20 as a. Okay, 20 is a, and b is 2, c is 0. See, c is 0 means where it will come, this is the point. Okay, c is 0 means this. So c is, you just recall, so when you plot, c is 0 means it is here. Okay, so it means that your graph will something like this. Is like this. Are you getting? The shape is like this, so that it is like this. Okay, because here we are discussing about young. Young is what? Connected with age. So here x-axis is connected with age. So age, anyway you cannot have anything less than 0. Okay, but starting from 0 you have to consider as young. Are you getting? Starting from 0 you have to consider as young. Okay, so this c is 0, and how much maximum we can take for young? So maybe 20, so that it is 20. Okay, so this is 20. And what is this b? Actually this b is talking about the slope. So this, how it should go when x increases, how the slope should change. So when the x increases, does the slope should vary very fastly, or it should come slowly, or how the slope should change? Actually here we are making the slope to change gradually, so that we give 2. Okay, so if you recall the bell curve, it is the formula is like this. 1 by 1 plus x minus c divided by a, okay, to the power of 2b, okay, to the power of 2b, that is the formula, to the power of 2b, that is the formula, okay. So when you plug here, what happens? 1 by 1 plus x, what is x is whatever the input, okay. X minus c is what? C is 0, so x minus 0 is 0, divided by what is a is 20, okay. 2 to the power b, what is b? B is 2, so 2 to the power 2 is 4, so that is how you got this, right? Okay. So similarly here old is defined like this. So old when you see this is a, this is b, this is c. So this is one way of definition. You can define in your own way, right? If you want the slope to go very steeply, you can do that. Okay. So here you see c is 100. So if c is 100, then how it would be? So c is 100 means so that is extremely old, okay, or maybe very old or very old, whatever it may be, okay. So c is 100 means that is this other end, okay. So 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 if this is the graph, then c 100 means it is, say this is x, okay. So 100 may be somewhere here, right? So from there up to how much point we are going to consider for old? So that is given by this 30. So that is c minus 30 and c plus 30. That is it is going to take 100 minus 30, that is 70, and up to 100 plus 30, okay. And here b is what? 3. Again this is the slope, right? So when you plug this to this formula, here c is 100, so x minus c, you get x minus 100, divided by a is 30, again b is 3, 2b is 6, right? Okay. So similarly middle aged can be defined like this: x 30 comma 60 comma 50, and so this is young means then not young, we can say it is 1 minus young, okay. That is whichever is not belonging to young, that is not young, right? So fine, let us stop here. We have discussed about the various membership functions and how it behaves in the context of fuzzy logic, right? So thank you.